Okay, let's go. Okay, so good morning, everybody. So my name is Wei Shang. So I'm an associate professor in Concordia University. So today will be the first event of our distinguished seminar series, and I'm very happy that we can have Dr. Bram Adams to join us. So Dr. Bram Adams got his PhD in Kent University in Belgium, and he did his postdoc in Queen's University in a cell lab. Right. So after he started his academia career, he started as an assistant professor in the Polytechnic Montreal, and then he moved to Queen's as associate professor during his associate professor, and he is so one of the pioneers to start this very important, very hot research topic, release engineering, and because of all their pioneers' efforts, so this becomes a very important aspect in software engineering practice, and is very widely adopted in practice. Um, and recently, he just received his MSR Foundational Award due to his contribution on the birth of release engineering research field. Right? He got various awards. He has very a lot of top publications. I bet everyone knows that. So today, I guess Bram will talk about his research in release engineering, especially in the current wave of AI. So I'll give the stage to Bram, and I'll let the seminar start.
Great, thanks a lot for the introduction, also for the invitation. I'm really honored to kick off the series this year. So thanks for that. So the coming 45 minutes, I'll be talking about the release engineering in the AI world. So not necessarily my own research, but basically also kind of explaining what is release engineering and what changes when you do that in AI world in order to get actually inspiration or kind of ideas to actually study these processes. So who am I? Well, actually, what has been said already, just a graphical summary. So I'm originally from Belgium, then I flew to Queens to do a postdoc, then went to Montreal, start my own lab on maintenance, construction, intelligence of software, and then did a position switch last year, moved the lab to Queens in Kingston, Ontario, and that's where I'm sitting today. So basically, here's the website of the lab, and we've specialized especially in release engineering, and as methodology to study release engineering, we use software analytics, also called mining software repositories. So if you're interested in more, please contact me. I can always provide more information. And also throughout the years, we've been involved in quite some events related to release engineering, in particular the Relenge workshop starting in 2013. Which attracted a lot of people, especially from industry, who kind of had done the major breakthroughs in release engineering, but still were struggling with lots of problems, lots of issues. And in these workshops, there were a lot of kind of discussions about those. Those led to two special issues in IEEE software. So a lot of things I'm going to talk today are based on things that were discussed there, but as well the newer things when AI comes up. Now, I've mentioned the term release engineering, and some of you might be saying, okay, what is release engineering? Please release us there. Well, basically, in a nutshell, I always explain as follows. I always say, look, it's basically bringing high quality code change from the hands of the developer into the hands of an end user and as quickly as possible. So this really touches on most of the aspects and sounds super simple, but of course, in reality, it's not as simple. And why? Well, because a traditional application, say a traditional web application, mostly contains code. So that's why I talked about bringing a code change to the end user. However, there was always also some kind of database and so on. Like traditionally, data has always been treated a bit as second-class citizen. In release engineering, there were things that worked, a lot of things did not work. But of course, when we now think about AI, data is a first-class citizen. Data is super important as the code, basically. And on top of that, you also have models. So now you have code, data, and models, and all three of them have to be released to the end user. So you might actually wonder, so yeah, how did this change, or how does this impact basically the practices in release engineering? So that actually leads me to the outline of today's talk. So basically, we first need to take a step back and think actually how release engineering went before AI, so like traditional web and cloud applications. Before we can then actually take a look in this new era of AI, what changes, what stays the same, what are the new challenges? And then that will be the second part of the talk. So let's go back in time before AI. We were all a bit younger then, especially in 2009. And why 2009? Because back in that period, there were quite some blog posts where people working in software, big software system at the time, were talking about statements like this. So this is the IMView application, which is like an online 3D chat world, like a web application had like 60,000 users at the time. And the release engineers of that system, they were actually putting statements like this one on their blog saying, oh, we release new code 50 times a day in 2009. So which means if you stay online 24 hours chatting away, then actually you've been using 50 different versions of the system without knowing it. Because that's important, without knowing it. You should not have seen that suddenly there's a new version. This system was not down, it always was up. And that caused quite a stir, these kind of articles. And these articles actually, they represent a new movement called continuous deployment, which actually at that time, what did they do? Basically, they like if there's a bug fix, developer works on the fix, commits it to Git. The idea is then that there's like some kind of phase, like quality assurance going on, continuous integration, CI, where basically 15,000 tests were automatically executed in 9 minutes using a kind of mini cloud. If everything went well, then automatically it would be deployed for the actual users. But of course, as I mentioned, they did not want the system to go down, so they did this in stages. So they started with like one data center, like a canary, they called that. They would put the new version there, while the other people are still using the old version. If everything goes well with new users using on that data center the new version, they would actually spread it out across the entire data centers. Otherwise, they would just roll back that one data center, and the majority of users would not have enough, wouldn't have noticed anything basically. And they could do that in 6 minutes, actually going from old version to completely 6 minutes if everything went well. So in 15 minutes and a time to fix a bug, you'd have 60,000 users having a new version without knowing it, unless they're really a big new feature or a crash, basically. So these practices really developed further. There was a very influential book, Continuous Delivery by Humble and Farley. And these practices really survived until today. And why? Many reasons. One of them, for example, you reduce the risk of releasing if you release often enough. Very interesting side effects and benefits of these ideas. So nowadays, these things still exist. For example, the term release train, a short cycle time between successive releases, they are still there. And what's also still there is that initial pipeline, those steps we saw to get this continuous deployment, these also have matured, and you have this kind of like standard release engineering pipeline, which looks a bit like this. So you start always with code change from developer. First is you need to integrate that code change into the overall code base so that it kind of there's no conflicts with the rest of the code base. Then you need to do quality assurance, make sure that, okay, textually the code might integrate, but maybe it doesn't compile anymore. Maybe the test fails. You need to test all of that and store the results in kind of artifact repository. And then once you're happy with a certain release, you can actually deploy and release this. So deploy means put that new deliverable where it needs to be, all the servers, all the cloud nodes where it should be. Release means make that thing that has been deployed visible to the right subset of users. So that they're not synonyms, they're different, but often like discussed together. And then you have live application. That's the idea. A very important thing here, you have this kind of sidetrack environment. So we have to talk about environment as well. And we will do that in a couple of minutes. Now, one thing you might be wondering, hold on, like quite a lot of these things, we've heard as well in the context of something called DevOps. What's DevOps? What's the link with release engineering? Well, DevOps is actually is heavily related, but is more like a process related in the sense that, so originally in a waterfall era, you have a customer asks a developer to do something, and then the developer throws it to the sysadmin or whoever deploys the thing. So one-way communication. Agile basically added like interaction between customer and developer, but still the result was thrown to the sysadmin, no communication. What DevOps do is, as an extension of agile processes, is actually also adding interaction between the sysadmin and basically the developer. So that is like a fully, so basically the developer won't do anything that doesn't deploy in the existing environment, for example. So that's basically what's going on. So in a way, if you look, you zoom out a bit on our pipeline we just showed. So at the input, the code chain, that really comes from development, the dev side. The live application, that's actually in operations, the ops side. So in other words, actually Reliance is kind of like in between DevOps, or in other words, actually an enabler of DevOps. You have to pass through Reliance to go from dev to ops. So in that sense, they're really connected together. And typically in DevOps process, you have a lot of like monitoring of production. That's really important. So that's really kind of like in common there between both. So you can give feedback to the developers to improve the design, the deployability, fix issues, and so on. So we discussed as well production and monitoring in this talk. And of course, all of this is heavy automated. So because you cannot release so often and so frequently if you cannot automate these things. Manual intervention really should be minimized. So there's hundreds and hundreds of tools available that do that. Okay, so we're still in the pre-AI era. So let's now look at these major steps and really look a bit what's the main thing that happens there, was the major challenge. And then after we check in the AI world, is it still the case or did it change? All right. So let's start with patch integration. So there, basically, the goal is really avoiding / resolving conflicts because you have your code change you did locally, and you want to get to basically the next release of the system. And the question is how you do that. So the idea is that you worked on a code individually. Now you need to bring it first, share it with your team members in your team's branch, basically. And there could be some changes because you change the line that somebody else has changed. That's a conflict. You have to fix it. And so anyway, so you work on a team. Nobody else sees your changes. Of course, you want actually your change to be visible to everybody. You want it to get to the master branch. So at some point, you need to merge your change with master branch. And if you're lucky, that works. Your things are compatible. So your code is in. There's some further changes happening. And at some point, you start working on actual release. There's some more fixes, and you're in the release. Nice, perfect, easy. However, of course, the big challenge is that there's other teams. And the other teams also do changes, and those changes might arrive in master branch earlier than yours. So by the time you merge, you might actually be changing the same lines, or those people might actually have removed the function that you're using, and so on and so on. So you get what's called a conflict. And basically, it's very effort. It's also effort to actually predict that there will be a conflict or to actually resolve once you know there's a conflict. So that's very difficult. It takes a lot of effort. And things get even worse if you actually rely on third-party libraries, and those libraries might have a new release at any time because they're other organizations. And then if one team actually adopts a new version, yeah, what do? Do you have to adopt it as well because maybe you rely on an older API, and so it gets even worse, these conflicts. So that's really the main issue here, integrating code. All right. Now, of course, I've simplified things a bit, but I really want to first talk about the big issues before AI, and then we can revisit things. Okay, so patch integration. Now, what about, quality assurance, CI? Well, basically, CI does semi-automatic quality assurance in the sense that eventually you want to get your code to the main branch, as you just saw, like the main Git repository. So your patch locally, or you say, let's push it there, that's all we need. But of course, if you have a bug in your patch and you just push your thing to everybody will see that bug. Nobody can compile or test your system that doesn't work. So you need some kind of quality gates. And typically you have a system like Gerrit and also a GitHub like a pull request and so on that actually allow you to do reviews, like human reviews and review comments. And at the same time, also automatic compilation and testing of basically your patch. And the special thing here is that this happens on the current version of the code base. So not the code base you started with, but the current one, to see if there's any conflict or that actually passed through the first phase there. And of course, if there are issues, then there's like a feedback to the developer. Hopefully these can be resolved. And if that's the case, then only then the patch can be accepted. So how does these things look like, these automatic build and test? So you have these dashboards and you can see passing tests, failing builds, sorry. Here we see like 2 commits that failed. looks easy. Okay, so you click on that, you see the log, you can know why it failed. Here's a failing test. Sometimes it can be a failing compilation. You can see the compilation error and so on. However, there's some issues, and one issue in particular is that people say, this thing is slow. So if during code review, we have to wait for the build to finish, it takes a long time. Developers start doing something else. By the time the developer gets the feedback, it needs to do context switch. So that's very kind of a common issue there. And so the question is, why is that? Is it really compilation that's slow? What's going on? So basically, if you take a look like what builds in general takes long. So build means compilation and test. So a local developer, usually it's quick, because usually local developer, you compile the whole thing once, and then you just compile the things you changed, incremental compilation, and you only test on a subset of the unit test. Basically, that's all the quick. However, CI cannot do that. CI is just to avoid incorrect build results. The idea is really to do the full compilation and run all the unit tests and probably also integration tests automatically. And even afterwards, but I won't go there yet, I even think that take longer. But the thing here is that really CI needs to do a lot of compilation and testing, and needs to do that on every commit. All right. So every commit, you have to do full compilation and all the tests, or big subset of the test. And even worse, they don't need to do that just say on Windows, but on different versions of Windows, also different versions of Linux, perhaps Android, iOS, Mac, and so on. For your system, not just one product, you might have a lot of different variants of your product. It also needs to be done on all these platforms on each commit. Also, you have special kinds of builds as well that do static analysis instead of compilation and test. So there's a lot of kind of build jobs that need to be done. And the worst thing is, of course, if you have a failure, then, well, there needs to be a fix. And that fix, again, needs to do all these tests. So you have what's called this kind of inflation of build. So here we see for all these different platforms, like all the different kind of test suites that need to be run just for one commit. And I'll pause a bit for dramatic effect. Okay, that was short. But anyway, so for all these kind of platforms have to be done, and that takes a lot of effort. So what happens in practice, that people actually start grouping commits together, and when the group is big enough or after a certain time limit, only then one build or all these builds are done on that group, just to save time. And of course, that works to save time if everything passes, but if things fail, then there's an issue because you don't know which commit is responsible for that failure. So these kind of things are really kind of challenges that are happening in the pre-AI world in terms of CI. All right, so that's nice. Now let's do a sidestep here. Let's go to that weird thing, that environment. What's going on with that? So what's an environment? So when you develop your system, you develop your application, and imagine you have an executable out of that. Well, the thing is, that executable by itself doesn't do anything. You need to have something below that in order to run your executable. In particular, you need to have the libraries, configuration files, operating system, hardware, the sensor, and so on. Only when you have that and you put your application on top, then you could run your system. So this could be a real server, could be containers, VMs, but you need that thing in order to run your application. And even more, you actually need even network connections as well to web services, just for your system to be able to work. That's the thing. So all of that is actually the environment of your application. Now, what was the trick here? The thing is that it's super important that in your whole pipeline, you actually use the same environment throughout. Because imagining you do all your compilation and tests on, say, Debian 10, everything works fine, and then you're going to deploy your build deliverables actually on Fedora 30. Well, all the confidence you had in your application in terms of the tests are successful is gone now, because actually you have now a different set of libraries or different set of library versions, maybe a different operating system, different configuration files. So it's very likely something will go wrong just because you change the environment underneath your application. So that's why it's super important that throughout, and even that's the dashed edge, maybe even the developers on their own machines, they actually have exactly the same environment as will be used during CI and deployment release. So that's super important from that point of view. There's another point of view actually that recently has gotten a lot of attention, is basically reproducible builds. So reproducible builds is basically when you should be able, if you give to the build infrastructure, say the same version of the source code, the same environment of the build, so the same compiler versions, and so on, and the same make files, end files, Bazel files, and so on, that if you run that and say 3 different parties do that, they all get exactly bit by bit the same executable. That's super important. Why vulnerabilities, for example? Because you could say, well, maybe hackers try to change the source code of a system to get some vulnerabilities in the system. Okay, that's one way to do it. Another way could be to actually manipulate the compiler that will be compiled the source code, because if you manipulate the compiler to instrument something in the source code during compilation, you had the same effect. And actually there are examples of that in practice. People just were for months and months downloading executables that had actually things instrumented because of a faulty compiler. So that's why reproducible builds is super important. And this can only be done if, amongst others, the environment as well as consistent throughout. It can be reproduced at will. So of course, this is difficult to do manually. And that's where infrastructure as code was invented, or the principle where basically, instead of manually configuring things, you actually design a programming language in which you kind of state the needs. For example, I need a database, I need a web server, the web server and database need to be connected to these ports, and so on. Such that when you execute that program, that actually it generates for you your environment. It generates a virtual machine, the container or the containers, connects them, and so on. And that, amongst others, allows to do reproducible builds, better testing. You can version control your code, your infrastructure code, because it's code, and so on. So that really was a revolution in pre-AI times of release engineering. Here's an example. If people are not familiar, basically this is to create a container. You start with a certain image, a certain Linux version with Python 3.4. You add a certain directory on top of that. Then you install Python dependencies in the thing in that environment you're building now. And you just tell, okay, when you start this environment, this should be the executable that starts it. And here you go, you have, if you run this in 3 different places, you will get the same image. And actually, in principle, one person builds the image and then people download and instantiate containers out of that image. So that's really was a revolutionary thing and a key ingredient of release engineering pipelines before AI came. Okay, so assuming we have that secret ingredient, then we can finally go to deploy release, which everybody, I guess, was expecting the main thing here. And so we already talked in the IMView example earlier on about canary deployment, where basically you first go deploy your code in one data center, see how it goes, and if things go well, then you only spread it out to the rest. So this is like one example of a variety of strategies to deploy your code. And the key ingredient here is actually illustrated by this anecdote by Chuck Rossi, who used to be the release engineer, the head of release engineering at Facebook. And basically, he told this anecdote that if he was doing an interview, he would always ask in some way to the person, okay, how do you upgrade your system right now, the one you're working on right now? And if they say, okay, well, first we turn off all the servers, then we put a new version, then we put everything up again, that was it, end of discussion. So the key thing here is that you cannot do or make new deployments by turning everything off. You have to keep the system up and incrementally in some way bring things up, which means actually you will have a certain transient period where you have 2 versions live at the same time. So your code has to be backwards compatible. But the code should be able to handle that, basically. The developer should know that, and that's why you need to work together with the people in operations, DevOps, to do that. Okay, so there are a bunch of these algorithms like canary, blue-green deployment. An interesting one is A/B testing, for example, where say everybody's using this version of the system, and then the new version of the system will have an interesting feature. And this feature, there's 2 ways to do it. And the developers cannot decide which one will be the best. So they devise an experiment. And basically, what will they do? Like a tiny subset of users will be redirected to variant A of this feature, and another subset to variant B. But 99% of users still the old version. They don't see that. And people don't know that they've been choosing for one or other. They think that's the new release and they use it. And then using telemetry metrics are being gathered to figure out basically which variant is more attractive to people. And imagine it's version A. So then basically that version A, that's the new candidate for the next release. And then you can use Canary or Blue-Green or anything else to actually make that the new release for everybody. So that's like kind of an empirical study, basically, with real data from real users, subset of it, to actually decide what will be the next release. That's A/B testing. So these things happen, but of course, there's a lot of kind of question that actually, even up to today, a lot of people in release engineering are struggling with. For example, how do you know the release is ready? Okay, so the people, there have lots of techniques. You look at the number of bugs that are being reported, test cases that fail, and so on. But still, that should be released. That's an interesting question. And even the other way around, you did the release. Was it a good release? And even worse, you're in the process of doing it. You just push the button to start the canary deployment, and then 10 seconds afterwards, you see all these metrics coming in. Is it good? Should we continue? Should we roll back now? Now we still can, and so on. So these are kind of things people are struggling with. And then of course also, okay, maybe we will release in a regular fashion every 2 weeks, every 3 weeks, but should we be 2 weeks, 3 weeks, 4 weeks, every 12 hours? What's the best cycle time? So there's quite some kind of higher level questions there that are people still struggling with right now, even without all the AI things going on. So that's an interesting thing to note here. Okay, and finally, you see that pipeline, and now we can see basically the monitoring part, because things are in production. Now you need to know what's going on there. So well, we're all familiar with these kind of things. Okay, it's slow, it crashes, you cannot access the site, and so on and so on. So how do people in operations, so like, what do they do? So the idea is, of course, that you want to somehow log what's going on. Okay, you want to get data about the system that's running, and either be able themselves, so the operators can fix it because there's a hard disk crash or something, or maybe no, it's a bug in the system and the developers have to fix it. But here's already feedback and context so that the developers could easily debug the issue. So that's really what's going on. So monitoring basically involves a couple of steps. So if this is your application in its environment, then you need to first decide what to log. So the developers on their side in the source code will add log statements to indicate what are the important events. The operators will instrument the environment. So for example, to measure hardware counters, kind of trace certain parts and so on. So, but of course, the more you put in, the slower your system will run, the more you need to store. So you have to like make a trade-off there to decide how to store stuff, how long. You will typically get textual data, logs, and numbers, metrics, and also need to correlate them somehow. So then there's a variety of tools that exist that basically use all kind of like machine learning, textual patterns, AI ops actually to identify issues. The system is running and there's so much data, so you need something to say, hey, here's something here, there's something there, to warn you, to notify you. But at the same time, there's a lot of work with visualization as well to actually see, to summarize the data and see patterns and easily say, I need to get more information about this thing, and then maybe look for patterns and so on. So there's a lot of things going on there just to make that work and to either resolve things locally or kind of give the right feedback to the developers, to this DevOps interaction. All right, so a lot of things here. We've seen actually traditional pipelines, what they tend to do, what they tend to like have issues with, what people tend to work on, and so on. But now, of course, AI. Okay, so what does that mean? Well, we already touched briefly on a key difference there. Actually, if you want to know really all the details and a lot more, I refer you to this blog post. Actually, it's a super long and very detailed post on Martin Fowler's website, but actually by these three people who actually a couple of weeks ago gave a presentation at the SEMLA talk as well. Now, and they defined and actually looked at continuous delivery for machine learning. So basically the thing you saw in the beginning, the continuous delivery from 2010, that book, but now revised actually in the machine learning era. And they kind of redefined basically what it means. And actually, a lot of things are still the same. So the last part of this definition is still about, okay, you want to make small increments, you need to reproducible builds, you should be able to release at any time. That's still the same as before. The key differences, though, is that now cross-functional teams. Suddenly there's cross-functional teams that need to produce this kind of thing, and they need to not just bring code changes to the end user, but code, data, and models. And that, of course, that creates a lot of new issues and challenges. So let's take a look. So basically what we looked at until now was the pre-AI stuff, and that was mostly code. All right, code, you have this whole pipeline, DevOps we talked about, and so on. Okay, but now, for example, we have data as well. And maybe, I don't know, maybe it's surprising, but actually in the data world, so the data science, data engineers, data storage people, and so on, they also have a pipeline actually, and you might know that as data ops. So what's this data ops pipeline about? Well, of course, there's again a lot of different ways of doing it. Here's like shows the essential thing, but there's many variants possible. But in some way, you need to first collect data in your organization, data from different sources, different formats. So typically now you put that in a data lake, which allows to do that and still find links between these different heterogeneous data sources. And then, but that at that point, you don't have a specific use case in mind. Okay, but then as soon as you have some kind of use case in mind, you start kind of project the data in a view, and that view will be more focused on a specific set of use cases. You need to clean the data, you need to transform it, the format and stuff like that, units and so on. I need to label it for that use case. And then for one specific application for that use case, you would then select the data and get a labeled data set. All right. So that's what people tend to do in that world. And they do that still now. And they need to do that because that's eventually how you get your machine learning model in a system. But so, okay, you don't have just one pipeline, you have two. And actually worse, you have three pipelines because, of course, surprise the model people, data scientists, mathematicians, AI people, and so on. They also have a pipeline, which you might call ML ops, actually. So what does this ML ops pipeline do? Basically, it starts with a labeled data set, which surprise comes from the data ops side. It will then actually come up with new features and so on for the really model-specific data set, train a model, perhaps multiple models. It will evaluate them. It will repeat that in experiments, try different hyperparameter values, all these kind of things, get different performance metrics. And eventually we'll select a model that, yeah, should be used and should be used either for analysis or for integration in a software system. But so this pipeline is doing that already and been doing that for a while. So if you think about it right now, instead of having one pipeline that does everything and so on the code, you now have three pipelines, and three pipelines managed by different people, cross-functional, as was mentioned. So the big challenge here is like, how do you integrate that? Because if you don't integrate those three pipelines together, you will never end up with high quality code and models in your application on time for the end user. So that's a big thing. So basically, how do you do that? Well, there's kind of four kind of big challenges here. There's of course more of these, like the four major ones, and I'll go a bit in more detail on each of these four. So these are the four. So let's start with the first one. Okay, and each one then we will see, okay, what actually worked already before in the world of code, and see if that is still manageable right now or new things are necessary. So that's the first one, team organization. So you might be familiar with Conway's law, where it basically says that, okay, if you look at a big software system and you look at its architecture, that might tell you a lot about how the organization behind it is actually organized. Because if you have three big components, probably were like three divisions, maybe in three different countries that work together and so on. So that's a known principle in regular software engineering. Well, here actually you get like in a bit of a similar situation, because here we have three pipelines that are done by different groups of people, different roles. Actually, you have the data people, the model people, the code people, and somehow, yeah, you could probably imagine that the way they collaborate probably might have a big impact on the success of these systems. For example, if you work in a waterfall way, so the data people do something, they show the data to the model people, they do some models, show the model to the software people, you get probably again with the same disadvantages as traditionally in waterfall development. So silos and lots of delay, no feedback, and so on. The other way around, if you do like the agile approach, where the whole team consists of a mix of the different roles, you get a lot more kind of collaboration. However, the tricky part here is that in contrast to, for example, developers and testers and the user who put together, here you have like people like, for example, model people who like to experiment with models and tweak and stuff like that, but then developers who need to deliver a product, stable product, experiment, so in the same team. So that could really cause kind of friction or things you need to really take a deeper look at. So there's this whole continuum between these two, and of course figuring out what's actually the best organization. It is like empirical studies of figuring out, okay, is this agile approach really better than the waterfall thing, or is it like a hybrid? There's a lot of work left in that area for sure. And then second challenge, reproducibility. So we already talked about reproducible builds before, okay? But somehow here, that was on code, okay? So build, so what about reproducibility of models? Well, that's maybe not as simple as it sounds, because if you go just a random dictionary, what does that mean? Reproducibility means to have consistent results when an experiment is repeated. So if you use infrastructure as code and Git and all these kind of things, then we've seen that, yeah, you can get with a bit of effort, like bit to bit, the same binary for code. That works. But what about the model pipeline? Because if you look here back at this MLOps pipeline, there's a lot of things that can vary because your labeled data set in the beginning, if you change slightly the data set, for sure you will get different models. Okay, if you change the set of features you extract from the data, same thing. If you change slightly the algorithms used for model learning, yeah, if you change the metrics, if you change the setup of the experiments, if you do a different way of selecting models, so all these things can vary and could really render your models, well, not reproducible, and actually just the fact that just take one deep learning algorithm, run it twice on exactly the same thing, and you always get slightly different results, likely. So it's challenging, actually. So a lot of things maybe you cannot control directly, but a lot of things maybe you can, if somehow you could just like version control these things. So you can have all the different versions of your feature engineering script or different version of your model learning script and so on. So that would be very helpful. And actually, these kind of things have been starting to develop. So the last couple of years, there has been like tools like DBC, MLflow, Pachyderm, and so on that really started come up with this notion, just like infrastructure as code, now you have pipeline as code. And so what does that mean? So for example, here on the right, we see like a simple pipeline where you have a script that prepares the data, like basically data ops. Then you have a script that does feature engineering, and then a script that trains a model. All right, and there should be invoked one after the other. So you have these tools like DBC that allow you to express this pipeline as a graph, basically saying, look, this is this node, and in this node we output a directory with the transformed data, and that should be the input of the next node, which is this one, which then takes a Python script that will output a directory with the features. Okay, and those features will be used by the last node, which runs a training script and outputs a model. So that's cool, and it's actually even more powerful because if you know like make files and build scripts and so on, they do like incremental compilation. Same thing here. These tools actually do incremental pipeline execution. So if you kind of run your pipeline, you have a model, then you tweak just the feature script, you rerun it. It will not redo the preparation step because that doesn't change at all. It will start with the feature step, the second step, and continue on. So it's like very powerful in that regard. So that's it. This kind of thing seems to address quite of some of the issues we showed with model reproducibility. But of course, the top node, because what is a top node? That's the data. So how do you kind of version the data? Because, well, one intuitive step would say, well, let's put it in our Git repositories, right? But would that work? Well, let's take a look. So if this is a Git repository, okay, and we have 6 files, A to F, okay, and imagine across time, we have different versions being committed of each of these files, and imagine file A is a data file, all right, just for a demonstration. So what does this give us? So on the plus side, our Git repository records which versions of each file were committed together. So you know, for example, that the red version of file A was committed together with the red version of C and F. So you can really understand a bit more the dependency between data and code and so on. That's nice. And even better is that actually you could have commits that only touch the data. And we've seen all this thing about CI and automatic compilation and tests. It's a commit. So this commit will trigger actually the CI to actually like not the compilation, but probably like do retraining of the data and followed by compilation perhaps, and then actually testing. So all this can be automatically done with existing tools pre-AI if you were only able to store data in the Git repository, just like source code. Okay, that's good, perfect. But on the bad side is actually that, you know, data is big, and technology like Git, what they do is they don't kind of store deltas. They actually store the whole, each version separately, compressed, but still. So that really kind of screws up the whole thing because it doesn't scale to Git. It doesn't scale to other typical code version control systems, it just becomes too big. And every time someone wants to check something out, everything is grinded down to a halt. So that doesn't work. It doesn't scale. So what happened then, actually, there's a lot of kind of technologies now out there that try to like do a hybrid approach, okay? Where basically say, look, put the data where it should be, put it in scalable, big storage, like in the cloud. You can have different versions there, no worries. You can have your code in Git where it should be. And you now have this missing link, so to speak, where you still have a file in Git that represents the data, but instead of actually containing the contents of the data, it contains like a remote pointer. It basically checksum of actually the remote storage. So every time you make a change to your data, you just update that pointer, that checksum in that file. You commit with any code that changes as well. So you still have the linkage between code and data through the checksum. And on the same time, the scalability is not an issue because the data is stored in a scalable way. So you have these kind of techniques out there. It also works for models. So it doesn't need to be data that's in there. You could actually put the models in the cloud and actually have a checksum that points to models and so on. So it could be any kind of big data, so to speak. You need to link with the code. All right. For example, again, in this example we showed in DVC, this is how that initial file looks like. So it doesn't contain the actual data, it contains like information to identify exactly what data it's referring to and to keep track of that. And that's how basically these modern technologies are doing. So you can actually have Git repository with only data, with only models. It's actually possible with this. Just have a bunch of checksums pointing to remote storage. That's nice. So there seems to be some kind of solution, although it's not perfect. We'll talk about later some issues, but so that's good. That's at least for the data we've seen. For models, you can somehow version them. What about the experiment? Because experiments played an important role in this MLOps pipeline. So basically, yeah, so the experiments, they actually, try for different hyperparameter values and so on to kind of see which one is the best, compare metrics and so on. And typically what you have, you start like with a base algorithm and configuration. You try, okay, what about this? It doesn't work. What about that? It's not good. Here, okay, this is some promise, but then, okay, maybe there's an alternative we thought of. So you really try to all different kinds of things. And it's like a kind of branching structure you develop in your experiments until eventually you get to the version you think this is the best one. This is what you want to keep. And you merge that into your system. But the trick is that all the missed opportunities, all the cases that did not work, if you throw away that information, you lose precious data, precious feedback, because later on, if there's an issue with the model you chose, and if you don't remember which experiments you did, you might need to redo all of them. So it's very important to keep track of your experiments. And that's something new, because in typical software engineering, experiments that don't really exist, right? So, but here they do, and they're like, again, like some kind of first-class citizen thing. So what can you do? So some tools, they store, they model this as actually branches, as we just saw. The old version of DC did that. Other versions, they actually say, no, don't do this. Just instrument your code, instrument your scripts that do experiments to log the information. So that in the future, if ever you wonder, did we do this experiment? You just query that database, the logs for the information. So there's different ways of doing that. But of course, instrumenting your code, it changes your code. It might have impacts in terms of quality and so on. So again, not much is known about that in practice, how that actually impacts development and quality. Of course, the actual models themselves, how do you actually deploy them? How do you release them? What's the typical thing? So the easiest approach is just take your existing application and environment and basically put in a model as a regular library. Just put it in as a regular dependency in your system and use it like that. And where do you find these model components then? Well, you have the notional model stores. So if you look online, there's actually just like app stores, you have stores for models. Like this one, for example, you see how many people downloaded them, how many people liked a certain model. It gets even like, this is AWS ML Marketplace. You actually see reviews of models. You see data about performance. So you shop, quote unquote, for a model, and then you use that in your system, basically. But of course, things can improve, and people have tended to actually move towards models as a service, where you don't put your model in your application, you put it in its own service, like a microservice, and then you contact that from your application or applications using a regular REST API. A big issue here, though, and that's where people are currently struggling with, it works terms of design, but in terms of latency, there's a big latency. If you have a smart device, you say something to it, by the time you get the answer, it's slow. Why? Because you have your voice, that data needs to be sent somewhere up. It needs to be kind of converted, processed, and then something is sent back, perhaps again, sound or video. Again, that takes some time. So a lot of kind of latency issues with that approach. Then, of course, you have the same idea with where the issue is, okay, now you have your containers of virtual machines, but you still have, say, 1 or 2 GPUs, and they all need these GPUs. How do you deal with these scarce resources? So again, there's kind of more advanced environments available that could exploit still the hardware and actually share it amongst different containers and virtual machines. That's also a thing there. Of course, you might say we don't have actually, we have Jupyter notebooks. What about that? Well, you can actually deploy Jupyter notebooks as well in specialized environments like that. It's not clear what are the actual long-term quality kind of characteristics of these kind of things, but you can actually, like for a quick win, let's say, put your Jupyter notebook directly visible as a REST service, and so on. So I'll skip this one because this is a bit too detailed, but just suffice to say, there's a lot of different ways and things people try to use existing pre-AI ways to deploy software, and now put models in as a component or as a service. And there's many other things people try, like A/B testing and so on, continuous learning, which actually is still a big issue. Reinforcement learning is also an issue in terms of how to deploy it in a good way. Now, and you might have heard about Edge AI. What it basically does is try to deal with that latency we talked about. So instead of having to send all your data somewhere to web service in the cloud, Edge AI, just like edge computing, tries to put these models, the execution of it, closer to the user. For example, Apple announced recently that the iOS new version would actually have models, voice recognition being run on your device locally instead of having to send it over because of latency issues. That is like a lot of kind of things people are looking at right now to deal with that issue. All right, and last but not least, how do you monitor your systems? You still have the same issues as before, and you actually have more of them. Because now you have models in your system. The models were trained on some kind of data. The data might be representative of your domain a year ago, but 1 year later, maybe people started to act differently and your model is not representative anymore. So data drift. You might have bias. Your models might be biased because the data was biased, your algorithm was biased. There's a lot of different kind of bias possible. So how do you observe and find out that it's biased? And how can you give feedback then to the right, I guess, the MLOps or the data ops people to deal with it? And of course, bad prediction performance in general. That's also an issue. So the big thing here is that, unfortunately, a lot of research is actually still going on for exactly these things, because there are kind of techniques to find drift and so on. But here it has to be run really in real time and really give exactly the right information as quickly as possible to the right team so they can change their thing, and then eventually as quickly as possible you get a good model again in a new version of the system. So there's a lot of kind of things going on right now on these specific issues at the operations side. These are big things. Okay, so to conclude there, what have we seen? We've seen a lot of things pre-AI that's whole to some extent post-AI, but with changes for data and models. But there's still a lot of concepts from pre-AI that we haven't discussed actually. Why? Well, we talk about build inflation. So builds take a lot of time, okay? And there's a lot of builds to be run. But now on top of computational builds, you also now need to do model training. And model training for different variants and so on. So you have even more inflation. How do you keep that scalable without having to do the same trick as they did before, like combining multiple commits for your builds? How do you do that? Yeah, there's no work on that actually. How do you review data and model changes? Okay, you review code changes. Okay, there's ways to do that and tools, but how do you do that for data and models? Like, not clear. How do you deal with streaming data? So not like just discrete data set, but actually data keeps on coming in. Can you version that? How do you keep track of that? Conflicts. Okay, we talked about conflicts of code. That's a big issue in the patch integration part. But now, okay, how about the data sets conflict or the models conflict, or how does that work? No work on that. Is the model ready for release? Because you talk, okay, is the code ready for release? Now, is this model ready for release? Again, like, and you have the model ready, the code ready, together they're ready, or they well integrated? Yeah, big question. How do you roll back like a newly deployed model? Is that as easy, quote unquote, as rolling back a bad version of the code? Because what happens when, for example, a database schema has been updated in the past, you make a new release and like new data is added in the new schema, it doesn't work, you have to roll back. So now you have data in the new schema, data in the old schema. That has been traditionally the big issue with data in release engineering. And since data and models are now first-class citizen, yeah, that's very unclear. So that's a big thing on that side in terms of release engineering concepts have to be reimagined. On the same time, and there's a lot more actually, on the same time also software engineering concept, because there's a lot of things that people are studying in regular software engineering, regular code and so on that actually could be revisited in this domain. So here's just some examples of work we did earlier. For example, co-evolution. So there's been a lot of work on how there's coupling between code and tests or code and make files and so on. But now you have not just all these code artifacts, you also have the data artifacts, the model artifacts, the cross-functional teams. So a lot of work is needed to just understand in terms of effort, maintenance effort, like how does that go? So a lot of work could be revisited in that area. And then another example is with work with Marius Volkhuis and his teams, basically, re-engineering. Okay, we've had all this work on re-engineering from say framework A to framework B, or programming language A to programming language B. But now imagine you now want to use these version control system like DVC and MLflow and all these kind of things. How do you actually migrate to that? Well, that's not very clear. So, but we've seen all these kind of things as software engineering that studies kind of concepts. So it would be actually interesting to revisit those, but in the context of release engineering for AI. And yeah, these are kind of just two examples, but a lot more that could be looked at. Okay, so to wrap up, basically we have talked a lot about the traditional release engineering API, the main steps, how it fits to DevOps and so on. Then we looked at continuous delivery for machine learning, where actually the main thing is really that you have two additional pipelines with cross-functional teams, and somehow you need to bring these things together because you have to get one product, like a polished product out of that with high quality and deliver that in a reliable manner to your end users. And then we also talked about a lot of things that held or had been figured out more or less for pre-AI. But now with data and models, you have to somehow revisit. And a lot of kind of possibilities to actually also study things that we're studying in software engineering, but in this context. All right, so these were kind of the main points I wanted to touch today, and I'm definitely open to any questions.
Okay, so I want to thank Bram for the amazing talk. Virtual applause. Okay, so if you want to ask your questions, so maybe so use the raise hands button. Yeah, so I will call your name and I will unmute you. I think you can unmute yourself as well to ask questions. Let's first Emad. Can you unmute? I'll unmute you, I think.
Cool.
Oh, you can. Okay.
Thanks, Bram, for a very nice talk. So my question was, and I think you touched on many of the important things, but one of the things that I find is super important, or a question that's frequently asked when we have these AI-based systems, is accuracy, right? And how do you ensure that when you get that new data set or your updated data sets, or your new model that you try out, how do you ensure that your accuracy of your model, or performance, if you will, doesn't go down? And of course, I'm sure you're familiar with the concept of model drift, right? But one challenge I think which is different even than model drift is the fact that as your system runs, since you have so many moving parts, accuracy becomes an issue. So do you have any insights on that, and how to ensure that there's mechanisms to make sure your accuracy doesn't go down, at least?
Yeah, it's an interesting question. Yeah, because it's definitely a major thing, and especially a major, and that something that makes it more difficult is that you have these different levels. Like, for example, like you have the code, the models, and the data people, let's say. So, so the first ones to actually notice these kind of issues when they're actually experimenting are the model people, basically. So they do all the experiments, and then they somehow will select models that for them has the best accuracy. But then, of course, you have the whole issue that by the time it gets into production, there's a lot of things happening, because that's first they give, say, hey, this is our best model, please take it, put it in the code. Well, maybe it doesn't work that well with the code, because the code somehow does something wrong, and the data it gets is different from the one it kind of expected in the model team. So there you already have one issue. And then the second issue as well, like at runtime with actual real production data, again, you have at that level kind of feedback. So you have these three levels of feedback, like the model team, when it integrated code team, and then in production. At all these levels, someone need to keep track of, like, how's the performance going? How is it kind of keeping up? Is it dropping? In for which subset of users is dropping? And right now, well, first of all, there seem to be currently used heterogeneous technologies. The models people using some kind of telemetry, let's say. The production team is sometimes using things. So that's one issue. However, most of them really what they're doing is really like logging. They're really logging and storing things. So like the model people will store for all their experiments, like the things that happen and how things evolved in the data. In production, like with MLflow, for example, people will actually keep on, with the regular logging, they actually will keep on logging the model performance in production. But then you really need this kind of AI ops technology to kind of really monitor things and detect things going down, because you have all these different ways. It could be periodically going, like for example during the week versus the weekend. It could really be like overall going down. It could be seasonal. So there's a lot of kind of patterns that could happen. So right now, apart from many kind of groups of people using heterogeneous technology, the main trick seems really to be to log things and then to have kind of strong kind of analysis tools around that to find patterns as quickly as possible. But yeah, it's definitely a big challenge, because what works in company A might not work in company B in terms of like drift patterns, for example.
Well, like, yeah, I would say that maybe my question was more about what happens in production, because you have a model, you test it out, obviously you're not going to push a model that will deteriorate your performance, but you test it out on your whatever data set you have in-house, everything looks great, you deploy that model, and now you have real life kind of data coming in.
Right.
And you don't actually there's not even a way really to validate, right? To say there's no ground truth at that point in time. Maybe you might have it the next day or in a year or whatever, in a week, but right then and there, you don't have any info. You kind of just fingers crossed it will perform well. But as you probably know, there could be different patterns, like Black Friday sales or whatever, where your model is not going to perform the way that it should, or according to what happened in the past. So this was really my question. I still find that it's very hard to validate that part, right? To know, okay, so is my model still accurate when I release it out to the world? And I think in a traditional software system, it's fine. You kind of, there's some predictability, but in these AI-based systems, I mean,
well, so I've seen like two ways in which companies are dealing with it. So one of them is actually in an indirect way. They have some kind of other metric or kind of thing. For example, is it like some kind of like Amazon style application, for example, that you would look at numbers in terms of sales and so on to see if they kind of matched with what the models predicted. For example, the thing predicted, hey, people tend to buy this when they buy that. Then do people actually buy that afterwards? So that's indirect metrics. That's something that's used. And the other thing is actually a delayed feedback, in the sense that, for example, in I don't know, like say a bank or something, you have a model that predicts something about credit card. Should this person get a credit card? Is that person able to finance it? Of course, if you wait long enough, you could get feedback to figure out, hey, the person, yes, was indeed able to pay for it or not. So that's the other thing. If the delay is short enough, you could actually also manage that. But for sure, yeah, it's not as like instant, like just, oh, the system crashes, because then you have instant feedback. So that's definitely a big challenge in the area. Yeah.
Okay, I think the next one is Dr. Rating.
Hi, Bram. Thank you for your presentation.
Great.
Now, I have actually two questions or two comments.
Great.
Are we actually going to recreate another software crisis like we had in the 60s, right? You know, in the 60s, people started developing these large systems and they documented it, but at the end, they lost the traceability, right?
Right. Mm-mm.
And nowadays, we look at 3 different ops models, right? We say, hey, we create snapshots of our data, of our models, we store everything, but at the end, is it becoming manageable? And are we just creating a new crisis? Are we actually fundamentally address the problem? I think we are just running always behind the curve, right? Patching and patching. We say, okay, we store, and then we analyze again, right? And try to recreate things. Shouldn't really be, as a software engineering community, should we address it from a different perspective? Maybe coming from a more formal method approach, integrating these models and just start really from a clean sheet rather than trying always to patch. My second question would be now, so is continuous integration dead?
Can you go a bit more detail on that statement? Because
because we're adding more complexity, right? The builds take longer. You have multiple resources who can change and merge.
right.
So if we had challenges before, right, things are not getting easier. But that was anyways also at the end your conclusion, right? So
Yeah.
do we have to go back to something where we have longer release cycles to get to make sure that we have stable snapshots? So are we going back to the past and then reinvent ourselves and patch it again and go some thoughts?
Yeah, so actually, based on what happened in the past, I'm sure we will reinvent ourselves at some point. But actually, so first on the second remark is CI dead. So the thing is, CI, the idea was that you get quick feedback about the quality of something. So of the code originally now like data models, so that the person responsible for it could quickly kind of, with things still fresh in the mind, kind of improve things until you get to the right level of quality. But of course, yeah, as you mentioned, and also as maybe with the inflation and stuff, the quick feedback, that part is somehow disappearing, and also the actual feedback itself, because if you have, say, for each commit, one build and one set of tests, and you have one outcome, pass or fail, that's easy to deal with. Because there's something failing and I have to continue until it passes. But now you have for that one commit like a bunch of like 100 different kind of and one of them might fail, or 20 might fail, and 80 might be good. So even the feedback is puzzling. Like you need a lot of tools, actually dashboards, to make things clear. And there, is CI dead now that you have all this variability for models and data on top of it? Yeah, so I still think like these clutches, like doing one build for a group of commits instead of per commit, will to some extent still work to some extent. Also, there's still quite some teams where the model people, they work on a different rhythm, a different release frequency on models than the actual code people. So at any point in time, the CI would be more on code changes, on more model changes. So it might actually in many cases still work in those things. But if things really wrap up and like lots of companies like do like all these kind of products with all these models, something will be necessary indeed to deal with the quickness and also with the quality of the feedback. That's for sure. And actually the first question, the software crisis. So there's actually many companies that actually, like if you look at the adoption curve of all these technologies and even models, like even AI, just the idea of, let's use AI in our product, they're still quite early. They still they just have one model maybe, and that one model might be trained like not just every week, but like every couple of months or something. So they still like can still oversee things, you can still manage things at that point. So but of course in how many years like they will be kind of like just like crazy model change. Yeah, and then there is a risk indeed that it's too much. Now I do think, since they're still starting slowly and in a manageable way, that actually will allow people to grasp things better and actually find some way to better kind of trace things together and better keep things together basically. But there's a risk. I agree with that.
because that's what I always think when I look at my basement, right? When I moved to my house, it was clean, and now I'm collecting more stuff, right? And I thought it was organized, and I don't find it anymore, right? And I think that's one of the issues people face, right? I personally think, we are starting a new sort of software, call it software data crisis, model crisis, anything, right? Really new software.
Yeah, especially we have all these different kind of frameworks to build models. Some of them are not surviving, others do, but they have different API. So add that to all these different, before we had different version of Java, let's say, now you have different version of TensorFlow. With that as well makes it much more critical to trace things together, basically, keep things manageable. Absolutely.
Okay, thank you.
Thanks for the question.
All right, thanks. So I guess the next one is Ahmed, then Hung. So Ahmed.
Yeah. Hi, Dr. Bram. Thank you for the nice presentation. Actually, I had a question about versioning the code, data, and model in different places. So, for example, we need to upload or push the code, for example, in repositories, data, and model in the cloud. So, do you think this could add an overhead to the developers to manage these repositories? And for example, if I want to get a certain information from a logs, right? I might need to go to different places to get it and explore different sources. So do you think this is a challenge to the AI teams? And I'm not sure if there is a way that they are dealing with it right now.
So yeah, thanks for the two questions. So for the last one, how teams are dealing with the log information. So that's indeed like a valid point. So that was mentioning earlier with Emat's question as well, that you have still these three different groups of people who might, to certain varying degree, be in the same team or in different teams, having their own kind of tools and log files and log libraries. And so there's of course a risk that you indeed end up with a data lake, let's say, of logs, basically. And then just like, because I think about like DevOps, the idea there was that you bring the operations people and developers people together, and so they use the same tools and they can help automate setting up environments and mining logs to get feedback.
Yeah.
So that was important. But of course now you have also the data ops and the model. So it's indeed important to kind of somehow synchronize all of them, but all of them have also slightly different needs, hence the different tools they use. So it's indeed a major issue there. In many cases, in different, like in the hierarchy of management, they might have different managers, so the different objectives. So all these things play a role. You also have other, like you have biz ops, like the interaction between business management and operations. So there's a lot of things happening there. So that's indeed a valid concern, that there needs to be some kind of common log or knowledge base to really keep things manageable. That's for sure. And regards to your first question, the scalability of having data in the cloud versus version control. So the thing is that these data sets are really quite big, like gigabytes or more and stuff like that. So the time it takes actually to upload something like that in the cloud versus the time it takes to have these additional text files with checksums that will refer to those things, that's much bigger. So it's actually the overhead in the Git repository is relatively low compared to basically having that in the Git repository where all the developers are impacted by things. So in practice, actually, it does scale quite well, this separation, and just keeping the link in the Git repository instead of the actual data. So that turns out to be something manageable there. But of course, it does force then the data model people as well to use Git, which could be a good thing. Like in terms of DevOps, that was also what happened with infrastructure as code, was also storing Git. But you might need to give additional training because the operations people had some kind of IT background, but the data ops people and ML people don't necessarily have a development background. So they might not be as fluent with these kind of tools as the developers and testers, for example. So that's then a training kind of issue.
Okay, good. Thank you.
Thanks.
Okay, Heng.
Hello, Bram. Thanks for the presentation. So my question was two questions. Actually, so do you think the models should be stored in the version control repositories like how code was stored, or do you think the models should be stored in the artifact repositories, like how executables libraries are stored. It feels like the model training process is like a code compiling process, and the models are like the compiled artifacts, right? And how about data? Like the second question is, how about data? Data is like the dependency, the environment of the compiler, it feels like. So what's your opinion?
Yeah. So your first question, that's it's like we have code and then the executable, so to speak, and now you have, say, the Python code that implements your learner, basically.
Yeah, right.
The actual model. So this is actually a good analogy, and actually that's how many cases things are handled. So the actual code that generates, that trains basically your model, that would actually also be put in Git. It's code, but then actually the models that are generated could indeed be stored in the artifact repository, and ideally you have this kind of checksum that refers to the artifact repository in your Git repository as well. So we need to recreate this specific release. Exactly, oh yeah, this was the kind of executable model, let's say, used here together with this. So that there things go well together as a kind of analogy, basically. But data, that's more difficult, because traditionally, before AI, application all had databases. So data technically was there already. So in your code, you talk to databases some way with a certain DAO kind of thing layer or something. So that was there. But the problem was that even then, there was already kind of this thing you use, but you don't get a hold of it. Like kind of as long as a new release does not kind of change existing fields in the database, for example, doesn't modify the existing schema, it just adds things. It works, like adding a new release. But even then, imagine you add a new field, you release. Yes, some users, they use the new version, their data is added in the new fields, and then suddenly there's a rollback. You roll back, and then you fix something, go back. Now, what happens now to the data that was added in those extra fields for these users? Is that data then stored during the rollback and is brought back, or it just is discarded altogether? So those people have to enter again. That already was like something that was very difficult to deal with even before AI. And now data is even bigger kind of role. Granted, the role is different in the sense that it's not like the data here is like database you query at runtime. It's data that's being used to train models and to retrain models and to evaluate models. So it's a different role. But yeah, there's still the issue how to deal with it. So it's not necessarily something like dependency, as like this analogy is not directly applicable, but it turns out that somehow, just keeping a link from within the Git repository to wherever it is stored seems to work in many cases. So this seems to be getting under control, as long as it's not streaming data, because there people are again not sure how to deal with that. But so models and code, there's some kind of similarity there. Data is the weird one. It's very flexible, very hard to manage.
Okay, so are people using like the ways how we store like the data in the database in traditional software engineering, or they are or they are like using different ways to store the data? I mean, so can they just reuse what has been used in database domain?
Technically, yes. I mean, you could always kind of use certain, because they have like NoSQL databases. If you pick the right one for the kind of data you have, you could actually do that and use that then during the training to that extent. The trick though, and that's also what I think Jürgen's question was about, is the fact that you need to keep things together. Like if you want to get in a reproducible way, like generate the same release in different spots, if you don't keep track, okay, where was the data that was used at that point in time to train this specific variant of this model for this specific version of the code, you lose that. And that's the big issue with kind of storing a data. Like it's hard to keep track exactly, okay, we use this specific snapshot of database at that point in time for this specific release. So that kind of traceability is easy to lose. And that's what a lot of people are struggling with, how to keep the traceability and still have a scalable way of managing things. Because the best thing would be put it all in the same spot, the Git, and that's it.
Okay.
But that doesn't scale. So traceability and still scalability, these are big things to find a trade-off between, actually.
Thank you, Bram.
Okay, so there's a question on the chat. So I'll read out the question on the chat first. So I think that's also related to Heng's question. So one of the recommended practices of software development is to develop through different environments, for example, development, testing, and production. However, on slide 32, you were saying that everything should be on the same environment. So what do you mean by that?
Yeah, so it's actually both statements are correct in the sense that, so the way I used environment is actually in terms of the specific versions of libraries, specific version of operating system, and so on. That has to be the same everywhere. However, what this statement in the chat refers to is more saying that, okay, before, say, you're developing something on that environment, that specific combination of library versions and operating system, you do that. So you not immediately say, okay, it's ready, up, let's now make it visible to everybody, which means let's now put it into production. So they have the same configuration of everything, but it's different location, let's say. So after development, where you locally tested it, you would then push it to the next environment, which is then a test, which will use the same operating system, same library, so same environment in my terminology. But that will be more people testing it. And if things are then ready, then you could push it, deploy and release it to the actual user in production, where again, the same operating system, same library versions were used, but now it's visible to the biggest group of people. So in that sense, they're kind of complementary, just refer to where that environment is compared to what's in the environment. So it's always the same thing in the environment, but it could be in different spots or different phases of the actual pipeline.
Okay, next question is Diego.
Hi, Bram. Thanks for the very nice talk. I was just wondering, in CI pipelines today of conventional software systems, we have a lot of problems with flaky tests, like tests that often fail and often pass non-deterministically. And these models are essentially non-deterministic. So I was just wondering, what are the strategies that are put in place to make sure that the CI go, and if essentially I can assume that most of the strategies would be about replicating tests and run tests more often, right? Which essentially mean that CI pipelines on those systems can be very expensive, costly wise, right? Because they have to run many times. What are your comments, and what are the strategies you've seen them like in place to avoid this?
Yeah, thanks for the question, because yes, indeed, that's what I should have added to the slide, because that's even another factor making the quality of the feedback of the CI even worse, in the sense that even when it says kind of a failure, it might actually not be a failure of your system. It could be a failure of, like, okay, there was just a glitch in the network connection, like stuff like that. And then, yeah, so in traditional CI domain, what are the ways to deal with that? As you mentioned, the fail-proof way, let's say, if you run it, rerun the build often enough, you might at some point figure out, hey, it was an inconsistent, means it was failing and then it was successful, which means this was a flaky test. Let's ignore that or do something about it. But the question there is even like how often you need to repeat, 100 times, 5 times, so that's why there's a lot of work coming up there, and actually the last couple of years to try to predict. Say, okay, well, it says fail. Is this a real failure or a flaky failure, basically? And then if that model says it's actually like a flaky one, then you don't need to repeat all these things and you save time, basically. So that's what most of the work is going to in that direction. But now, as you mentioned, yeah, now what about flaky CI when in the AI world? So, well, according to me, well, you already have the existing flakiness that's already there, for sure. But probably you will get even more because, yeah, maybe there was something with the data, or maybe there was just by chance the wrong kind of random thing here in this algorithm, and unfortunately there's no work whatsoever on that. So I think people are actually still trying to just run regular CI with data and with models, just get that working first, and they're not yet at that stage of like, oh, what if it now failed, but actually not a real failure. So there's no easy answer actually for the moment. So I think one thing will be to, because that's also, I think, how a lot of work started on flaky tests in the pre-AI world, is actually people doing empirical studies of actually CI results, especially flaky test results, to figure out what are the causes of these. So I think probably the first thing to do was really be in this now AI world to actually study builds from these kind of systems and really try to understand, A, like how common are flaky tests, B, why are they flaky? Is it just because the same reasons as before? Or is there now like new reasons of flakiness related to data and models? And if there are, and you understand those, to then try to find ways to deal with that. But there's no quick solution apart from this longer research one to my in my opinion right now. So if you're looking for a research topic, I think that would be a great topic to look at. That's for sure.
Thanks for the answer. Yep.
Okay, I guess next question is from Alec.
Hey, thank you, Dr. Bram, for the instructive presentation. I actually had a question about releasing. So usually we want to release something that's, as you said, traceable and kind of easy to roll back and in small patches. Mm-hmm. So when it comes to applications that actually have AI in them and have different models, do you think it's a good idea to release only changes with the models, only changes with the code separately? Or is it still okay to kind of release code changes and models together? Which one would be easier to roll back and trace back in case something bad happens?
Oh, so interesting question. So there's a lot of things, because actually, so before the whole AI thing, so for example, we looked at the product like Amazon or any other kind of similar big web application. Basically, like I said, that one website actually consists of like hundreds of tiny microservices that are talking to each other. And why was this done? Because originally other systems would not have this fine-grained thing. It would be more a monolithic kind of application. They did that because then every team could independently decide when and what to release and kind of like go quicker that way. Of course, keeping in mind, okay, there are a lot of people depending on us. We can't just break the API because that's a disaster. But so develop more autonomy basically for these different development teams.
Yeah.
So now in this AI world, so especially when you look at these ways to serve models as their own service, you actually get the kind of equivalent where I have these microservices that are the models themselves, and then other microservices contacting them to get a prediction. So in that sense, actually, that allows these model teams to actually have autonomy, and again, similar to before, decide do we have a new release or not. So in that sense, it could actually still work as before to have, okay, you have the more model-centric team here and a more code-centric team there. Of course, with some mixture of roles as well. But the big problem is that it's much harder to know the impact of things, because like if you change your microservice, the way that could impact others is a more systematic manner. There's okay, I changed this API, these people are using the API, and then these do that. But with models, things, what happens if your model, like, to determine what other people should buy, there was a bug and now you fix it, and now there's a whole other kind of area of products that are being recommended than before. That could really cause big changes that are harder to express as just looking at the API and control flow. So that is the thing that's not clear yet. Sure, from the organization point of view, you can give each team their own service and let them more or less independently release. But from the actual business point of view or kind of hidden data flow point of view, that's not clear. Is it a big impact or not? So that's again one of these things that over time there might be enough data to study that. But so in principle, we could use what was there before. They could release independently. In practice, there might be a hidden cost, and that's more tricky.
Thank you for the answer.
Okay, so we have another question from Filippo. Then another question from the chat. I guess we're almost out of time. Go ahead.
Thank you for the great talk, Bram. It was really interesting. My question is the following: do you think, having in mind repositories, do you think that DVC is going to become a standard de facto like Git?
That's always a risky question to answer, but so I think, well, let me answer from a different point of view. So I think the kind of repository like as DVC represents, so which basically enables traceability between code and other artifacts like data model, I think that kind of thing will be in the future indeed something you need, just like people need something like Git now, for sure. Is DVC the one? For sure, DVC is one. There's a couple of open source ones like DVC. MLflow does certain thing that DVC does as well. You have Pachyderm is open source. Then there's actually a couple of commercial products as well in that there. So it's early days. It's hard to say which one will survive, which one will be. But right now DVC for sure in terms of open source is quite popular and have a very active development team. But the actual product will win, I don't know, but we will need these kind of things for sure in your basic arsenal of development tools. That's yes, I would say yes.
Okay, thank you.
Okay. Okay, so I guess the okay, so I guess Sohaib, you're the last question. Okay, so I'll read out the question first from the chat. So first, are there existing tools integrating these pipelines already? For instance, Jenkins. And second, could be these pipelines integrated in huge software systems like Facebook, where there are hundreds of commits daily and huge amount of data.
So the second question for sure, because like Facebook, Google, LinkedIn, and so on have been integrating models for ages, like a long time, let's say. In there, and they have learned, they have developed their own tools. Some of them were open source. So I'm not worried, let's say, about the big kind of organized that much. Although they have, of course, there's inflation of builds and stuff like that. But they've invested a lot of money, and it's more, I think, like the rest, like the other 99% of companies, or even more, that might be big, might be small, how do they kind of all these technology, all these things fit together? Like how can they learn that and B, adopt what they need to be successful without being overwhelmed and just do something that they actually don't need or they don't understand. So I think that's for the second thing. For the first one, yes, there's a lot of these tools that are getting kind of traction as like plugins for Jenkins or other kind of CI things. So of course, like things like Travis CI, I don't think right now there's something yet doing that, but there are efforts underway of going there. So right now it is possible, yeah, with existing open source CI things to glue things together. Maybe not yet in like plug and play, let's say, but it's definitely possible to do that. And it will improve over time, without a doubt.
Okay, I guess the last question is from Sohaib.
Cool. Thank you for letting me asking the question. So I have a question about like the randomness in training and creating these AI models. There's a lot of parameters. Some of them like based on random seed, and then you create some kind of parameters, and there's another side of hyperparameters that you try randomly through the training model. And these things can affect the accuracy of the model. For example, if you say like, yeah, if you train like random foresting and the depth of the model, how many nodes and these things, every time you train it, you could get different parameters and different things in these stuff. How this should fit in the release engineering part and keeping track in these and how you should like even use these things before, for example, modifying stuff on the structure of the pipeline of the training and these stuff, and to have a clear idea what the thing that make the effect. Is it these randomness or structured or like concrete thing that change in the pipeline?
Yeah, I think the answer will be controlled chaos, actually. Let me explain what I mean. So basically, if you go back pre-AI, like I mentioned, the reproducible build. So the issue there is the following: so that the developers have finished their code, and to get from the code side to like a binary that users use, the idea is that you just run the build thing and you get the execute. That's it. But of course, the big problem is that there might be kind of parties in between that like do something, they modify the binary, they modify the compiler to inject vulnerability, basically. So, which means the binary you get is not like a one-to-one translation from the actual code. So what happened in the past is that there was a big issue because organizations were aware of the issue, but they were not able to test, to check whether their pipeline was safe, because just even without intervention by a third party, run twice your pipeline on the same version of the code and you would get two different binaries. Why? Because GCC would include like a timestamp in its every executable file. They just code that would use random numbers as well and add some random versioning number, the build number. So whenever you run the thing, you always get different binary just because of that. So there has been a lot of and still ongoing effort to actually make the actual current build pipeline deterministic. So no more timestamps in executables, no more random numbers, build numbers in the actual build product. So that took a lot of effort just to be able to say, look, now we're sure if all goes well, you always get the same bit-to-bit kind of the same output basically for the same input. So now whenever we want to check whether anybody intervened, we can do that. So that took a lot of time, but basically controlling chaos. For example, for random numbers, they could, for example, always use the same seed for the same kind of version of the code. And so they have randomness, but it's always starting from the same point, so you get the same output actually in the same build. So I think now in the AI world, where you have all these algorithms, and yeah, by default they also do the like weirdest things. Yeah, so well, first of all, I think like it's probably super ambitious to do this bit-to-bit comparison right now with all these models. So is that really scalable? That's another thing. But one way to deal perhaps with it is doing the same trick, making things more deterministic within the same run. So for the same version of the code and the model code, use the same random seeds and all these other tricks to actually try to get the same bit-to-bit output. But that's easier said than done. It took ages actually for regular quote unquote software engineering. Actually, 2014, I think I was in a conference, the FOSDEM conference, open source, and the Debian people doing the build. They were doing a presentation that they had been working for years there, and they were still not at 1% to actually making their own build deterministic. 7 years ago, I think they finished a couple of years ago. Others started out, so it takes a long time just for that without AI. So it's super ambitious, but for sure it's something that will need to be thought of, especially for vulnerabilities. Like if you try to add the vulnerabilities to a model, like it's possible actually. So yeah, or like do all these kind of weird training things with models to give them other output. So it's definitely a major issue, like security wise. But a good start could be what worked for software engineering, and then try to better understand the unique challenges of the actual models.
Thank you very much.
Thanks for the question.
Okay, so I guess let's thank Bram again virtually for the great talk, and we had very nice discussions in the past half an hour.
Yeah, thanks a lot for all the questions.
Okay. All right, so thanks everyone for participating in this seminar. So the seminar will be, so the plan is to have this seminar every month or every 2 months, depends on the schedule of our invited speakers. And we'll keep you guys updated for our next event. So thanks everyone. Bye.
Bye.